Let's look at an example. We had our sales promotion example where the percent increase in sales was a function of whether or not it was a promotion, indicator for one or two promotions, and there's comp sales as a third variable. Our null hypothesis is that all three betas are zero. So the intercept is not zero, but everything else is zero. That leads to a reduced model, percent change equals beta 0 plus epsilon. So this is an unusual hypothesis in that all of the coefficients are zero are hypothesized. So what we have in this special case, that since the model that we are left with is the null model, we already know the sums of squares of the null model. The sums of squares of the hypothesized null model is the sums of squares total. Yeah. I'm gonna go back one slide. Remember that this model basically says I'm modeling the response with just one parameter, and the estimate of this parameter turns out to be the average under least squares. So I only have the average in there, and that means that everything that's not the average is in the error, and that's the total sums of squares. Okay, so I already know the sums of squares. It's the total sums of squares. For the full model, I also know the residuals. It's the sums of squares error. Well, I know it when I have the output, right? So that means that in this particular case, I get in the numerator, where it takes the difference between the two, total sums of squares minus error sums of squares. Well, and we had seen in the ANOVA that that's just the sums of squares regression. So we have sums of squares regression in the numerator, appropriate degrees of freedom, and sums of squares error as we always have in the denominator. Okay, so here's a question for you. What are P and Q in this particular example? So I'll leave you to answer this question, and I'm moving on to the next slide. We had 30 observations, right? And so the next question for you is, what are the degrees of freedom for the F-test, where I'm writing the formula up here. We have the numerator and the denominator degree of freedom. And I have some answers here. So I will let you answer this, and I'm moving on to the next slide. Here is the output from the regression. And here we see, well, this is new for you. This F-test is already implemented in the data output. And the probability associated with it is 1%, 1.37%. Okay, so over time, we will learn what all of these things down here are: R squared, adjusted R squared, and root MSE. We now know the ANOVA, we know number of observations, and this F-test here, this is the corresponding value, and this is the corresponding p-value. This is the statistic and the p-value. We just learned this just now, and these three we catch some other time. And down here, you also know everything. So you know everything except for these three numbers here. All right. So given that the probability from the output is below 5%, and we often use 5% as the significance level, we reject the hypothesis that all betas equals 0. Or we can also say reject the hypothesis that the model has no effect. Mind you, this is a very, very weak hypothesis. All we are saying is that there is something in the model that's not completely random. You'd hope that the model has at least some explanation power, because otherwise, why are we modeling? All right, this is the end of this segment.